Please, I hope I'm audible.
Yeah, you're audible, sir.
Okay. Okay. So let's please can you see the empty sheet?
Yes, I can see from my end here.
Okay. All right. So I think if you can see that, then I guess everyone else can also see it. So I believe we are good to begin. All right, so today we are going to be talking about a couple of things. So we'll be talking about comparators, then after comparators, we'll look at multiplexers and then demultiplexers. So I think I spoke to Mr. Prince to allow DCIT 203 throughout next week. So as it stands, I believe that throughout next week we'll be having a DCIT 203 section. That is from Monday to Friday, and within that period we'll cover a lot. So those sections will be aimed at wrapping up on combinational circuits, sequential circuits, and we'll also look at automata. Okay, and then after that we can say that we are okay and set. All right. So to begin with, I think we've looked at others, we've looked at subtractors already and everything before that. So I don't think it's convenient going back to them again because of how little a time we have. So today let's go straight to comparators. Okay, so if we're able to complete comparators and multiplexers, demultiplexers, then on Monday we will look at encoders and then decoders. And then after looking at encoders and decoders, Tuesday we'll look at we'll move to sequential circuits. And then there we are going to look at for sequential circuits, we look at flip-flops, we look at latches, and then we looked at counters, registers, and I mean everything else that we are supposed to look at there. So please, you shouldn't worry, we'll cover everything left within this week. All right, so let's look at comparators. So when we are talking about comparators, it's just a basic thing we know about comparison. Okay, the name is derived from comparison, that is to compare. So comparators are basically used to compare inputs. So when let's say you have three inputs, let's call them inputs A, inputs B, and input C, and you don't really know which input to pick, a comparator becomes necessary. And we'll talk about their practical application also. Okay, so a comparator becomes necessary. So based on a given logic, which we are going to discuss, a comparator would then give you a corresponding output. All right, which are going to take the form, a comparator takes n number of inputs. It can take 2 inputs, it can take 3 inputs, etc. So let's stick to the 2 scenario, which is the ideal number of inputs for comparators. We'll clarify that when we move forward. So ideally, the inputs can be 4, they can be 8, etc. But they are still classified into 2 blocks of inputs or 2 groups of inputs, which are input A and then input B. Okay, so the corresponding outputs are going to be a comparison operator, which is in the form A equals B. So it first checks for equality. Then after equality, it first checks if one input is greater than the second, or if one input is less than the second. This is the basic function of a comparator. So taking that again, we said that it takes n number of inputs. Let me write that. So it takes n number of inputs, which is n. So what we mean by it takes n number of inputs is that the inputs that a comparator can take always varies. It can be 2, it can be 4, it can be 8, it can be 16, or even 32, etc. But then when it comes to the output will always be 3, regardless of the number of inputs it takes. And the 3 outputs that is going to return would always be in the form A equals B, A is greater than B, and then A is less than B. So if you are asked that, let's say, a comparator with n outputs, okay, so how many outputs does a comparator with n inputs have, or how many outputs will a comparator with n inputs have? The correct answer would always be 3, okay, because we said that the basic function or duty of a comparator is to compare its inputs and return an output, a comparison output, okay, in the form A equals B, A is greater than B, and then A is less than B. Aside these 3, there is no other output combination for a magnitude comparator. So if you are asked, let's say A minus B, let's say you are given A minus B, A greater than B, etc., and you are asked to select which is not a correct output of a magnitude comparator. Of course, you know A minus B will be it, because a comparator does not perform subtraction. We've already specified the type of circuit that performs subtraction operations. And we said that is either a half subtractor or a full subtractor. But then if we are performing comparison, we want to know if one thing is bigger than the other. If it is equal or it is less, then a comparator is very necessary, or a comparator is essential for such operation. So now you know what a comparator is. Let us look at the types of comparators that we have. Now, a comparator is classified based on the number of inputs it has. We don't really look at the number of outputs, because we said the output is always constant, which is these 3 things. That's equality, greater than and less than. All right. But then, as I said earlier, the inputs can change. You can have 2 inputs, you can have 3 inputs, you can have 4 inputs, you can have 8 inputs, whatsoever number of inputs. All right. But then the output would always remain the same and unchanged. So then, to name or to classify comparators, you usually look at the number of inputs it comes with. And based on the number of inputs, we can classify them as 1-bit comparator, okay? So you can have a 1-bit comparator. And what a 1-bit comparator does is that it compares 1-bit numbers. It compares 1-bit numbers So what we mean by one-bit numbers is that we are talking about numbers whose inputs are only made up of 1 bit. Okay, so either 0 or 1. And then we have a 2-bit comparator. 2-bit comparator kind of functions quite differently because it compares, please, the function is the same, but then its behavior is quite different because it does not compare 1-bit inputs, but rather it compares 2-bit inputs like 0 and 1, and then 0 and 0, or 0 and 1 and 1 and 1. So whenever the bits that you are comparing are 1, you use a 1-bit comparator. Example, when you are told to compare, or when you are asked that which comparator will be used to compare, let's say, input P1 equals 0 and P2 equals 1. And you are asked the question that which comparator is needed to compare this input combination, you are going to need a 1-bit comparator because you can see that all the inputs are made up of only 1-bit binary numbers. Okay, but if you are giving, let's say, P1 equals 0, 1, and then P2 equals 1 and 0, then this is going to be entirely different because you realize that the inputs are 2 bits. Okay, so you have 1 bit here, another bit here, so 2 bits in total. So please, for this, which type of comparator do you think we are going to need to compare this? Can someone help us?
Please come again.
All right. So I was saying that, hey, we are only 3. I was saying that assuming we have inputs P1 equals 0, 1, and then P2 equals 1, 0, each input is made up of 2 bits. Which type of comparator are we going to use to perform this comparison operation? Are you going to use a 1-bit comparator or you use a 2-bit comparator?
A 2-bit comparator.
A 2-bit comparator is needed to perform this kind of operation. All right, so let's continue. So he said that we classify comparators based on the number of inputs that they come with. So if we have a 3-bit comparator, it means that you have something like P1 or your A, okay, to be 0, 1, 1, and then your P2 or your B to be, let's say, 1, 0, 1. Okay, so you can see that each input contains 3-bit numbers, and this helps us know the exact type of comparator that you are going to use. So to represent or to draw the block diagram for this particular set of inputs, we can have our comparator right here. So this is how our comparator looks like. So we have a magnitude comparator, and then we know our inputs are 3 bits, right? 3 bits each. So we have 0 here, 1 here, we have 1 here. And all these 3 are classified as what? P, as P1. And then we have another 3-bit combination, which is 1, 2, 3. So this is 1, 0, 1. So we have 1, 0, 1. And that is all these 2 is our P2. All right, so the output you said are only going to be 3. So the first output is going to be P1. Is going to compare if P1 equals P2 or is P1 lesser than P2, or is P greater than P2? I mean, is P1 greater than P2? So if you realize how we were doing the comparison here, or how we stated it, we said that is P1 equals P2, or is P1 lesser than P2, or is P1 greater than P2. So what does this tell us? This tells us that the basic comparator, okay, or the basic logic gates that is used for comparison is our OR gate. We use our OR gate for comparison. But take note, there is an issue with using the OR gate here. We said that with the OR gate, it returns true if at least one of your inputs are true. So even if you have 1 and 1, your OR will result in 1. Okay, so 1 or 1 will still give the 1. So you don't want this. You want to eliminate this. So if you want to eliminate this scenario, then you have to use an exclusive OR or an XOR, because an XOR gives us a true comparator. That is it only compares 1 and 0, and then 0 and 1. It eliminates the case of 1 or 1 and then 0 or 0. Okay, so this is the two things that we seek to compare. So the basic comparator, okay, that is used for magnitude comparators is our XOR gate, or the basic logic gate that is used for magnitude comparators is our XOR gate. So please let's take note of this. In the examination, you can be asked which logic gates or what is the basic comparator, basic logic gates used for magnitude comparators, or which logic gates is used for comparison operators in a magnitude operator. Please, the answer is an XOR gate. So let's move on. So this is our block diagram for a 3-bit magnitude comparator. All right. So this right here that we see here is that of a 2-bit magnitude comparator. All right. So assuming here is 0, 0, and here is 0, 1, then this becomes a 2-bit magnitude comparator. But if it's just 0 and then B is 1, then it becomes a 1-bit magnitude comparator. All right, so let's move on with this. I hope we are okay so far.
Yeah, that's fine, sir.
All right. So let us look at the truth table for a 2-bit magnitude comparator. Okay. Well, let's first look at a 1-bit magnitude comparator. So 1-bit magnitude comparator, the truth table. When it comes to 1-bit magnitude comparators, you know that it only takes 1 B. It only takes 2 inputs, right? And you know the inputs are always going to give you are always going to be classified into A and B, right? So you have A and B, and then your corresponding outputs will be classified in the form A equals B, A less than B, and A greater than B. So these are the basic headings you are going to have. Okay, so you know that your inputs can be a combination of zeros and ones. So you have 0, 0 right here. Then you can have 0, and 1. Then you have 1 and 0, and then you have 1 and 1. Okay. So now these are our input combination for A and B. A can be 0, B will be 0. A can be 0, then B will be 1. A can be 1, B will be 0. And A can be 1, and then B will be 1. So if we have these input combinations, let us compare A and B, starting from the first one. So 0 and 0. Let's ask ourselves, is 0 equal to 0? Is 0 less than 0, or 0 is greater than 0? So let's
0 is equal
look at
to
that.
0.
So 0 is equal to 0. So you put a 1 at that place. Okay. Then we come to 0 and 1 and ask ourselves, is 0 equal to 1? Is 0 less than 1, or 0 is greater than 1?
0 is not less than 1.
All right.
It,
So
0 is less than
0 is less than 1. So we put a 1 at A is less than B. Then we come to 1 and 0 and ask ourselves, is 1 greater than 0? Is 1 equals to 0, or 1 is less than 0?
1 is greater than 0.
1 is greater than 0. So we put a 1 here. And then we come to equality and ask ourselves, is 1 equal to 0? Is 1 less than 0, or 1 is greater than 0?
1 is equal to 1.
1 is equal to 1. So we put equality here, and then everything else will automatically be 0. So what does this basically tells us? This basically tells us that at any point in time, for the output of a magnitude comparator, only one comparison operation can be high. Okay, and this is a question that you can easily see. So, and just know this is a simple fact. For at any given input combination, only one output can be high at a time. The other possibilities will always be low, or will always be 0. Okay, only one can be 1. So if you check the first line, you can see that only A equals to B was high. If you check the second line, only A less than B was high. If you check the third one, only A is greater than B was high. And if you check the last one, only A equals B was high. Everything else were zeros. Okay, so let's kindly take notes of that point, or that fact also with comparators. So this gives us the outputs for that. Okay, so from this, let us derive our Boolean expression from this. So to derive our Boolean expression, we do the same thing we did for other combinational circuits, like truth, full adders, half adders, half subtractors, full subtractors, etc. So we said that we look at the output values that are high, which is this one and this one, and we ask ourselves, what are the corresponding input combinations? Okay, so just look to your left and ask ourselves, what is the A and B values when A equals B was 1? So you can see that the A and B values are 0 and 0. So if you are writing that 0 and 0 in terms of A and B, how are you going to write that? Can someone tell us?
A bar, B bar.
A bar, you have A bar, and then B bar, okay. Then plus, then you move to the second combination. So the second combination, that's which return a 1 was a 1 and a 1, which is A equals 1 and B equals 1. So how do you write A equals 1 and B equals 1?
AB.
AB. All right, so we've now exhausted all scenarios where A and B was equal to 1. So you can say that this here is A equals B. Okay, that's the corresponding expression for A equals B. So we can proceed to draw our logic gates diagram or our logic circuit diagram for this. And to do that, we have two different expressions here. And each of these expressions are product terms, right? You know, here, this is a sum of products expression because you have two product terms, okay, here, bonded by a sum right here, which is a plus. So let us work this out. So we have the first product term to be A bar and then B bar. So which logic gates are you going to use to implement A bar, B bar?
AND gate.
Can someone tell us? We are going to use an AND gate. That's very true. Because you can see that this is an AND operation. Okay. That's a product term. For all product terms, you always use an AND operation. So this A bar and B bar. So you have your A right here. Please, there are several ways to draw it. You can decide to use vertical inputs, etc. So whichever you want to use is you are correct. Okay, so you have B bar. Okay, so you have A bar and then you have your B bar. So the outputs of that, and then we have a second AND gate, right? For A and B. And here the inputs are A and B. So we could just decide to do this right here. So you have padding for that. So you have your A here, you have your B here. Let me just erase this. And so we are going to pick A right from here to here, okay, and invert it. So let's do that properly. So we use a NOT gate right here. And then we pick A from here, invert it, and then we get A bar. Okay. So we get our A bar. And then we can also take B from here and then invert it. So we have our, then we pick from here, then, oh, so we have right here. All right, so we've now been able to implement our A bar, B bar, and then our AB. Okay. So you realize that these two product terms are connected together with a sum or a plus, okay, which is an OR gate. So we join these two together using an OR gate. So we have the OR gate of those two inputs, okay, and that is going to give us A equals B. Please, I hope you all got what we did just here.
Yes, sir.
Okay, so the Boolean expression, okay, for A equals B is implemented using two AND gates and one OR gate. So let us just know that fact also. So the Boolean expression of A equals B in a magnitude comparator is implemented using two AND gates and one OR gate. So we are going to repeat the same thing for the others also. So let's repeat this for the others also. So we have A is less than B. So with A is less than B, we have to look at which output combinations return a 1. Okay. And for that, we can see it only happened here, right? So at that point, which input combination can we trace it to?
0 and 1.
0 and 1. Okay. So 0 and 1, what is it going to give us in terms of A and B?
A bar B.
So we are going to get A bar and then B. So implementing this is quite direct and straightforward. So which logic gate are you going to use to implement this?
Is it an OR gate or?
Yeah, we are going to use an AND gate because you can see it's A and B or A times B. Okay, so we are going to use an AND gate right here. And then you have a bar and then B. Or you can also prefer to say A, B, and then decide to invert your A. Some might also prefer to go this way, but all is just the same thing. We are going to get A bar B, okay. So same thing. Either you just go with this way or that way. You are correct. So after that, we look at our greater than. So A greater than B. We can see that the only time it returned a 1 was our combination C, right? So combination C, what was the corresponding A and B for that?
1 and 0.
1 and 0. So in terms of A and B, how do you represent that?
A B bar.
A, B bar. So we have A, B bar. So A, B bar, you can also use an AND gate. And then we have A, and then we have our B. So this impedance A is greater than B. All right, so after you've done this, you can connect your three together, okay, using universal input. So your universal input, are going to be A and B. So we can decide to, because that's a common input for all the three diagrams. So we'll draw our A and B. So you can draw your A here. So you have your A right here. And then we need the negation of that. So not A is going to be here. And then we have our P right here. And then we denote its negation as P bar. Then we go right here. Okay. So right here we have A bar. And then here we have B bar. Okay. So for A is greater than B, we said we had A, right? So we had this right here. So let's draw this here. And then we had A as our first inputs. And then we had B bar as our second input. So we have first input here, second input here. And then the corresponding output was our A greater than B. Then the second one, we had this right here, an AND gates. And then the first input was an A naught. So we take the negation of A, and then we have our B right here. So this was our A less than B. Then the third one, we had our A and B, right? So the first circuit was A naught and then B naught, right? So let me see. We first had an A bar and then B bar. So let's represent that A bar and B bar. So we first had A bar and then B bar. And then we had
So is it A bar B or A bar B bar?
the first one for this. Let me see. Yeah, it was A bar, B bar. That's for equality. Remember, the first one, we had a 1 here. So the corresponding input combination was a 0 and 0.
Yes,
I don't know if you recall.
Yeah, I recall.
Okay. So this is going to give us this right here. And then we had another, which was AB, right? So AB, you pick A from here, and then our B from here. And then that gives us our AB, okay? So after that, we combine these two using an OR gate. And that will give us A equals B. So this is how to combine all the three circuits in one diagram. All right, so this is for a 2-bit magnitude comparator. So I believe we've looked at everything with regards to 2-bit magnitude comparators, right? You've done that, right? All right, so let's move on. Let's move on. There's another thing with this. Okay, so there is another way you could have done this. Let me just mention this. So for equality, if you remember when we were looking at full adders and full subtractors, I said something here that whenever you have A, B, okay, and one of them has a prime on top, plus you have an AB, and then the opposite alphabet here, the B had a prime, but here the A rather has a prime. This right here is an XOR gate. Please remember that. And I also said that if you have this here, which is A bar, B bar, plus AB, then this right here is equal to an A XOR B. Okay, that's an XOR operation of A and B. Okay, so please always remember that. So you can also implement A equals B using an XOR gate. If you were to use an XOR gate, it would have simplified the third circuit as this. So this whole thing would have been simplified as an XOR, which is this right here. So you would have had A X no B. And this right here would have also been A equals B. Okay. So when we started, I stated that equality, that's A equals B, can always be implemented using an XNOR gates, because XNOR gates are considered as universal comparators. All right. So when we move, okay, you'll get there. Okay, you'll get there. So when you get to sequential circuit, if you look at some things under these same brackets, also, I mean, this same principle of concept. All right. So please, do you have any question? 2-bit magnitude comparators.
No, sir.
All right, so no, this is a 1-bit magnitude comparator, not a 2-bit comparator, magnitude comparator. Sorry. So if you were to work out a 2-bit magnitude comparator, let me illustrate how to work with that quickly. There is a short way to things, but I don't know if you would be okay with it. I would have just illustrated that for you. Okay, but that's if you not get confused. Please, we want us to proceed with the shorter ways to things. Else, you might have to draw your truth table before you can proceed with everything, okay? But I kind of believe that for the sake of examination, you might not really have the time to draw all those things. Since you are dealing with MCQs and time is not to our advantage, okay? You can decide to, I mean, not even draw the truth table, and you can still get your answer correct. All right. So for the benefit of the doubt, I would illustrate the concepts, and I'll also use a truth table for that. So let's use a truth table first. So for a 3-bit magnitude comparator, we know that, a 2-bit magnitude comparator, we know that the block diagram is like this. So we have a 2-bit mag. So 2-bit magnitude comparator. We know our inputs are going to be 4, right? So we have 2 here, 2 here. And the reason why I like separating it is because the first 2 will always be classified as A. And then the second 2 inputs will always be classified as B. Okay. So you have inside here, you have A0, and then you have A1. And here you have A2, and then you have A3. Okay, so you have 4 input, but I said that the output will always be 3. So you have 3 outputs. The first being A equals B. The second will be A less than B. And the third will be A greater than B, as we've already illustrated. So if we want to proceed to draw our truth table, then we know we are going to have our inputs. Okay, so we have A0. All right, so to make it easier for us, let's do this. So we have A, and then we have B. So under A and B, oh, so this properly. So under A and B, we have A0, and then we have A1. And then under B, we have oh, please pardon me. You can use A2, A3, etc., but that will be very, very, very ambiguous and make your work. All right, so since it's B, let's name this B0 and B1 instead. Okay. So here under B, you have B0, and then you have B1. All right, so to perform the comparison, you know that our outputs are going to be to take the form A equals B. Please let me get rid of this right here. Let's make this look a little bit that one. All right, so we have A equals B. That's 1. We have A less than B, and then we have A greater than B. All right, so now that we have this, let's look at our input combination. We know that we can have, we have a total of 4 different variables, right? So with 4 different variables, we know the number of input combinations that we are going to have, right? Please, how many input combinations are you going to have? Can someone tell us?
4.
Please come again.
4.
Are you sure? So this is a general rule, okay? When you are dealing with truth tables, if you have, please, there are exceptions to this. The exception is when you are looking at decoders and encoders. Like let's say the BCD to decimal encoder, that one, this has no hold. All right, so the general rule usually when it comes to drawing your truth tables is that your inputs, if you have n inputs, your number of input combination is going to be 2 raised to the power n. Okay, so here, how many inputs do you have? You have input 1, which is A0,
So
input 2, which is
16.
A1. Exactly. So you are going to have 2 raised to the power 4, which is going to be 16 combinations. So with 16 combinations, you can have 0, 1, we have 0, 1, 0, 1, 0, 1. This is 8, right? So we have 0, 1, 0, 1, 0, 1, 0, and then we end with 1. Okay. So 0, and then we end with a 1. Okay. So here we have 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Here we have 0, 0, 1, 1. Then here we have 0, 0, 0, 0. Then we have 1, 1, 1, 1. Then we have 0, 0, 0, 0. Then we have 1, 1, 1, 1. Then here we have 0, 0, 0, 0, 0, 0, 0, 0. Then we have 1, 1, 1, 1, 1, 1, 1, 1. Okay. So this is how to represent our input combinations. We start from the right side. The right side is just going to be 0, 1, 0, 1, 0, 1. Then the one before that is going to be 0, 0, 1, 1, 0. Then the one before that is going to be 4 zeros, 1 ones, 4 zeros, 1 ones, then 8 zeros, 8 ones, etc. So now that we have this, let us perform our comparison then. Okay. So let's perform our comparison. You see, we've classified the input into A and B, right? You can see that. So the first input are classified as A. So A here becomes A0 and A1, which is 0, 0. And then B becomes 0, also 0, 0. So now A, which is 0, 0, and B, 0, 0. Do we say A equals B, A is less than B, or A is greater than B, which is 0, 0 equals 0, 0. Is 0, 0 less than 0, 0, or 0, 0 is greater than 0, 0? Yes.
Equal.
Equal, exactly. So equality, we put a 1 there. Then let's come to the second one. We have 0, 0, and 0, and 1. Would 0, 0 be less than 0 and 1, equal to 0 and 1, or greater than 0 and 1?
Less than.
Less than, so we put a 1 here. So this takes a 0. It takes a 0. This takes a 0. This takes a 0. So we come to the third one. So 0, 0, and 1, 0. Will 0, 0 be less than 1, 0, or 0, 0 be greater than 1, 0?
It will be less than 1, 0.
Less than. So at less than, we are going to put a 1, and the rest will take zeros. So let's come to the fourth one. 0, 0, and 1, 1. Will 0, 0 be lesser? Will it be equal to or greater than 1, 1?
Less.
Less. So we put a 1 at less, and the rest takes 0, 0. So we come to the next. We have 0, 1, and 0, 0. So will 0, 1 be equal, lesser, or greater than 1, 1?
Great.
Listen again.
Greater.
Greater, good. So we have 1 here, and then you have 0, 0 here. So we are at where? So we are at 0, 1, and then 0, 1. So 0, 1, and 0, 1, are they going to be equal, lesser, or greater?
Equal.
Equal.
Equal. Yeah, so we are going to put 1 at equality, and the rest will take 0. Then we come to the next combination, which is 0, 1, and 1, 0. So 0, 1, 1, 0, is it going to be lesser, greater, or equal?
Equal.
Listen again.
Equal.
Equals. Please, let's look at that again. So we have 0, 1, and then 1, 0. So would this be, is this lesser than, or this is equal, or greater? Let's look at this again. If we say equal, we have to compare the first bit. You can see that the first bit here is 0. The first bit here is 1. So you see they are not the same. So for it to be equal, the first bit has to be the same. The second bit also has to be the same. So here you realize that even the first bit are not the same. Here is 0, here is 1. So that means it cannot be equal. So you have to look at greater than. So
Yeah,
it's lesser than. Perfect. So for it to be lesser, you can see that the first bit here, 0, is smaller than 1. So immediately you're able to spot that the first bit is smaller than the first bit here. Then it's lesser. Okay, if the first bit is greater than the first bit here, automatically it's greater. If the first bits
But
are
then what?
equal, you compare the second bits. Okay. Now, please, when you're done, I'll show you a shorter method out. And this is a shortcomings of magnitude. One of the things that makes magnitude comparators difficult. The more the inputs increases, the complex your circuit becomes. Okay, and the complex is truth table. All right. So if you have anything from 2-bit magnitude comparator, personally, I don't recommend doing all this in examination. It will take your time, real time. By the time you realize, I mean, you've wasted a lot of time. So I'll show you a shorter method out. If you're able to catch it, you wouldn't have any problem with working with any type of comparator. So we said here is lesser. So at lesser than, we put a 1. The rest takes a 0. So we have at what combination? 1, 2, 3, 4, 5, 6, 7, 8. So we are left with 8 more, right? So let's go to 1 and 1 and 1 and 1. So 1 and 1 and 1 and 1, is it equal, greater, or lesser than? So we have 1 and 1, and then 1 and 1. So do we put less than, greater than, or equal to?
Equal to.
So we put an equal to, because 1 and 1 is equal to 1 and 1. So we put an equal to here. So let's go to the next. We have 1 and 0 and 0 and 0. So let's speed up a little. So 1 and 0, 0 and 0. You can see that 1 and 0 is greater than 0 and 0, right? So at greater than, we put a 1. And then the rest takes 0. Then you have 1 and 0 and then 1 and 0. That's equality. So at equality, you put a 1. And then the rest takes 0. I'm coming on. Probably, I think we did 1 and 1 and then 0 and 0, and then I'm coming here was what? This was a equality, which is 1 and 1. Then we came, so we dealt with 1 and 2, 3. We had 0 and 1, 1 and 1. This was lesser. We had 1 and 0, 1 and 0. This was greater. Then we came to 1 and 0. No. Here is 1 and 0, 0 and 1. So this is greater, not equal to. I skipped that combination. So we were here. That's 1 and 0 and 0 and 1, right? So that's greater. So we put a 0 here, a 0 here. Then now we can come to 1 and 0, 1 and 0, and then 1 and 0 now, right? So that is equality. Then we now come to 1 and 0, and then 1 and 1. 1 and 0 is lesser than 1 and 1, so less than. Then we now come to 1 and 1, and then 0 and 0. So that's also greater than. So we put 1 at greater than. Then we come to 1 and 1, and then let me see. That's 3. So 1 and 1, and then 0 and 1. That's less than. No, 1 and 1 is greater than 0 and 1, so greater than, we put a 1. So we come to 1 and 1, and then 1 and 0. 1 and 1 is greater than 1 and 0, so we put a 1. Then we come to the last one. We have 1 and 1 and 1 and 1. That's equality, so we put a 1 at equality. Okay. So we fill. Oh no, I'm coming. So we fill. That's right here. So we fill the rest of the bits with zeros. All right, so this is how the truth table is going to look like, okay? And you realize that it's quite tedious, and the probability of making mistakes is very, very high. So when you are done with it, you now have to come and look at all the ones that returned a 1, and then minimize using a K-map, okay? So here, because the ones are quite a lot, you cannot take the A, B, C, D combinations, because you are going to have a whole lot of like lengthy, complex equation, okay? So what you do is that you use a K-map directly to perform the minimization. So you separate this into, let's say, two groups of 8, and then you draw a 4x4 K-map. And then on the 4x4 K-map, all the first group of 8 are going to go into your first 8 cells, and your second group of 8 are going to go into your second 8 cells, okay? And then from there, you can perform your minimization. So if you intend to use your K-map, you would have something like this. Let me add one more division. So we have 1, 2, 3, 4, 1, 2, 3, 4. Yeah, so this is a 4x4 K-map. So you have your A0, A1 here. So A0, A1. Then you have your B0, B1. Okay. So here is going to be cell 0. Here will be cell 1. Here will be cell 3, cell 2, cell 4, 5, 7, 6. Then you have your 8, 9, 11, 10. Then you have your 12, 13, 15, 14. Okay. 4, 4, 5. Here will be 7 and 6. So you just arrange your ones here according to their position, and then you do your minimization. All right. So now let me show you how you can be able to obtain the correct values without even drawing your truth table, or without going through the hassle of drawing your truth table. So now let us look at how to work with that. So please, let's pay attention to this. So we have our A, and then our A contains 2 digits, which is a combination of A0 and then A1. And then we have our B, which also contains 2 digits. We have our B0 and then B1. And we know that the outputs are first going to be for A equals B. We said A equals B, then we come to A is less than B. Then we come and look at A is greater than B. Because I believe we all recall this, right? That these are the 3 possible outputs scenarios for a magnitude comparator. Please, we all agree with this, right?
Yes.
All right, so if we agree with this, then we can proceed to make our deductions. So we said the first scenario is equality. So we have to compare if A0 and A1 is equal to B0 and B1. So now let us look at this. So if you have 2 bits binary numbers, like let's say 0, 0, 0 and 1, okay, etc. In which cases would they be equal? They can only be equal when the first bit is the same as the first bit and the second bit is the same as the second bit. Please, we all agree with that. That's 2 bits binary numbers can only be equal if the first 2 bits is the first 2 bits for the first number is the same as the 2 bits for the second numbers, the second number. So please, I don't know if we can see that or we are confused.
Yeah, we get it.
Okay, so if we take the case of 1 and 1, compare the first bits. You can see that the first bit is 1, they are equal. Then compare the second bit. The second bit is also equal. So you can conclude that this set of combinations are equal. Okay, so there are only 2 scenarios where 2-bit binary numbers can be equal. It is 0, 0 for A, when A is 0, 0, and then B is also 0, 0. We can say that these two are equal. Or when this is scenario 1. So scenario 1 is when A is 0, 0, and B is 0, 0. Or when A is 1 and 1, and B is also 1 and 1. Apart from this, there is no other scenario again that 2 groups of 2-bit binary numbers can be equal. We all agree with this, right? Please, do we all agree with this? Or
Yes.
someone has a problem so that we clarify? Any questions so far?
Yeah, cool.
Cool. Okay. So we said that the only 2 scenarios where 2 binary numbers made up of 2 digits each can be equal is when your A is 0, 0 and your B is 0, 0. If you compare, the first bit is equal, second bit is equal, the numbers are equal. First bit is equal, second bit is equal. They are equal. For instance, if you take 0 and 1 and 0 and 1, they are not equal. 0 and 1, and let's take 1 and 0. Okay. We cannot establish equality here. All right. But then if we are to take 0 and 1, yeah, this will work. So if we are to take 0 and 1 and 0 and 1, yeah, we can also establish that this is equal, right? Because the first bit binary number is equal. The second bit binary number is also equal. So we can say this is also equal. So this is a third scenario. So the first scenario, or also have this 0 and 1 and 0 and 1. So if we have this, then we can also have 1 and 0, right? And then 1 and 0. Because 1 is equal to 1, 0 is also equal to 0. Now, aside this, for no other scenario exists where equality would hold. Okay, so if you come back and then you are to cross-check, you would be able to verify that from your truth table. All right. So with this, we can now deduce our expression from here. So we said that here, A is 0, 0. So if A is 0, 0, what is it going to give us? Please, can someone tell us if A is 0, 0, what that is going to?
The question again,
Is if A is, okay, so if A is 0, 0, okay, in this context, we know that the first 0 is A0, the second 0 is A1, okay? So how do we represent A0, 0, A to be 0, 0 in the form A0, A1? I don't know if you are getting me. Now we have A to be 0, 0. We know the first bit is our A0, second bit is our A1. So A0 will be A0 complements and then the second number will be A1 complement. Please, do you agree with me?
Yes, yes.
Exactly. And the B, is B0 and B1. So that's also complements. So B0, B1 complements. Okay. That's scenario 1. So scenario 2, we said or, and we know or is addition. So we say plus. Then scenario 2, we said 1 and 1 and 1 and 1. So 1 and 1, that's going to give us A0, A1 plus A. A0, A1, and then B is also B0, B1. So or, then bring our plus again. Then come and look at the third scenario. That's 0, 1, 0, 1. What is it going to give us? Please, what is 0, 1 going to give us?
0, 1.
Yes, please.
0, 1 will give us B0 and then B1, B0 prime and then B1.
Please come again.
So for 0, 1 for A, 0, 1 for
Okay.
A will be A0 prime and then A1.
All right, so we have A0 prime and then A1. And then for B, we are going to have what?
B0 prime B1.
So B0 prime and then B1. Then we have plus, then the last combination. And then we are going to make an interesting reduction after this. So the last combination.
A0, A1 prime. Then B0,
Right, so
B1.
okay, so we have A0, A1 prime, and then we have A0, A1 prime, right? This is the case, right? So you see, all what we've done here if we are to do some simple insertions here, for example, we know that A0, A1 is equal to A, okay? So that means we can represent all this with A. And then B0, B1 is equal to B. We can represent all this with B. So A0, A1 is A, so we can represent all this with A prime. And then B0, B1 is B, so we can represent all this with B. Okay. Can you tell me what we are having here? You see, we now have this situation AB prime plus AB. Please, isn't this very familiar? We just talked about a concept when we're looking at the 1-bit magnitude comparator. Okay, with this particular combination here, and we talked about the same thing when we were looking at full adder, half adder. Please, can someone help us? What does this represent? A prime, B prime plus AB. What does this represent?
XNOR. A.
It's an XNOR.
Yes,
That's exactly the XNOR of the inputs. So you can say this is A XNOR. You know, you write XNOR this way. So we can say this is A XNOR B. Okay. So we can directly say here that this here is A XNOR B for this. And then we can make that same deductions from this side also. Okay. And look, if you remember very well, we have a principle of redundancy, and that is one input cannot repeat itself 2 times. Please, do you all recall? one input cannot repeat itself 2 times. So you have this case right here. You have, please, I didn't write this correctly. So you have B0, here was B0 and B1. So you have A0, A1. So the A here is prime, B here is prime. And then you literally have the same, you literally have an inverse of that same thing repeating itself here. Please, can you all see that? Please, can you all see that here? All right, let me illustrate properly. Please, a second, let me illustrate properly so that I think it's because the thing looks very messy, so you are unable to see through properly. So let's have that illustration right here. So you have A0, A1, okay, and then B0, B1, and you are adding these two, A0, A1, and then B0, B1. This takes prime here. Here, let me see. B here is prime, here here is prime, A here is prime. So if we decide to replace, let's say, what do we replace? Let me see, you have A0, A1. Okay, so we can see this right here, right? We can also see this, we can see this right here. So please, who can tell us what this exactly represents? If you remember, I told you something about having this A, B here plus another A, B here, and then this takes a prime. Please, can you recall this problem? And what, yeah, this represents an X or, okay. So please, if you study this carefully, you can see the same scenario occurring here. You can see that in the first product term, which is A0, A1, one of the input combination takes prime, a prime. But if you look at the second product term, it has that same thing, A0, A1, but it is rather the A1 which takes the prime. Then you see B0, B1. Okay, here the B0 takes prime. Then if you come to the second one, you see the same B0, B1, but here it's rather the B0 that takes the prime. Okay, so you can see that that is the same scenario here, but just that here, the number of variables are 4, but here the number of variables are 2. Okay, so if you have this kind of scenario forming, it reflects an XOR gate. Okay, so this right here will be an A, X, or B. Okay, so we can reduce this whole thing to just this A, X, or B. Okay, so from this, we can make a conclusion that for a 2-bit magnitude comparator, A equals B will be the X, or we will compare with an exclusive or for all its input variables. Okay, so that is for A and B. So for A1 and then B1, they are going to be an XOR of each other. And then for A0, B0, we are going to have a similar thing right there. Okay, so there isn't even a need to have to go through the process every single time. You just have to know that equality is always an XOR operation. Okay, please, do we get that? So whenever you are dealing with magnitude comparators, we said that equality is always established using an XNOR instead, not an XOR. Okay, so it's always established using an XNOR. Please remember I stated this earlier. Please, do you all recall that I stated that for equality we use an XNOR exactly? So please, whenever you are dealing with A equals B, don't bother yourself drawing through tables, etc. Just take an XNOR operation of all the inputs given. So for example, if you have 1-bit magnitude comparator, that is A and B, your A equals B is going to be the A X or B. Okay, X or B. So you are going to have A, then an X or B. So just do same when you have 3 input variables or 4 input variables. Okay, so it is just going to be the external operation of your inputs variable. So this basically is how a magnitude comparator works. It just takes, compares, and establishes equality depending on the number of inputs that you have. Okay, and then we also have our multiplexer. So our multiplexer works quite differently from a comparator. A comparator performs comparison operations, okay, but our multiplexer kind of does something different. So let's look at what multiplexers do. So what multiplexers do is that, or how they operate, is that they are used to select one input, okay, which is then routed to one output line. So you are going to have your max right here. So let's say this is your multiplexer. Assuming we have a total of 2 inputs, you always have a selection criteria, okay, which is called a selector. So here will be let's call this X0. So our X0 is our selector. That is what you use to select, or that is like our switch. That is what is going to send our selection signal, okay, or that's our select line. Let's call it that way. And then it has one output. So that one output, let's call it Y. And then our first input, let's call it D0, which is data line 0. And then the second, let's call it D1, which is data line 1. Okay. So this is how a max operates. We have multiple inputs, and then it only sends out one output based on the particular signal that our selector sends. Okay. So this is how to know how many inputs a particular type of selector has. And for this, you will certainly see a questions and that in examination. So for instance, you'll be told that a selector has, let's say, one select line. So a selector has one select line. How many inputs does that selector have? Okay. So to determine the inputs that particular selector has, we are going to look at 2 raised to the power the number of select lines. Okay. And that is going to give us the number of inputs carried together, where n is your select lines. So instead of n, you can use x, but n is equal to your selectors. All right. So assuming that in the diagram that you are given, you can only see A0, so you have only one select lines. So To find the corresponding number of inputs, you are going to take 2 raised to the power 1 because our select line is only 1. Hence, how many inputs are you going to have? You are going to have 2 inputs. That is why in this diagram, you can see that this particular multiplexer has only 2 inputs. Okay. So let me give you another question and then you tell me the answer. So you have a multiplexer which has, let's say, 2 select lines. So you have S0 and then you have S1. How many inputs would that multiplexer have? You have a multiplexer with 2 select lines. How many inputs
4.
Or how many data lines are we going to have for that particular multiplexer?
4.
4. Okay, so we are going to have 4. So we have D0, D1, D2, and then let me put one more here. So we have D2, and then we have D3. Okay. So this is how it's done. So based on the number of, based on the number of outputs and its corresponding number of inputs, we are going to, and its number of select lines, we are going to name, and its number of outputs, sorry, we are going to name our selector. Okay. So for example, this particular selector, we are going to call it a 4:1 max. So a 4:1 max is any multiplexer which has 4 inputs and 1 corresponding output with 2 select lines. Okay. Sometimes you can be given the select line, the inputs. For example, a selector has inputs 1, 0, 1, 1. Okay. So let's say a selector has input 1, 0, 1, 1. How many select lines? Why am I calling it selector? A multiplexer has input 1, 0, 1, 1. Okay. How many select lines will that multiplexer have? Or how many select lines are we going to have for that particular multiplexer? Please, can someone help us with an answer?
2.
Yes.
2.
Please come again.
2.
2, that's perfect. So we are going to have, or we are going to need 2 select lines or 2 selectors for this particular multiplexer, because you can see that the inputs are 4. We have D0, D1, D2, D3. So we need to ask ourselves that 2 raised to the power what is going to give us 4, which is the number of inputs. Okay. So you know our n will be 2 here because 2 raised to the power 2 is equal to 4. There's another way to determine this. You can take a log base 2 of your whatsoever, but I don't think we might want to be doing that. So you have 2 raised to the power n equals 2, and then you'll be able to, if you're able to find your n, which is 2, you know that the number of selectors that will be needed for that particular multiplexers are 2. Okay. So now let's look at the truth table. Interesting enough, when it comes to multiplexers, their truth tables are very, very, very simple to work out, irrespective of the number of inputs you have, because it follows a particular pattern. Once you understand the pattern, you are just good to go. All right. So let's look at a selector with 2 inputs. That's a max with 2 inputs. So a 2:1 max. Okay. Let's look at a truth table for a 2:1 max. And once you're able to get it, this, or the technique here, you should be able to get your input for every type of multiplexer. So you have D0, you have D1, then you know you are going to use only one select line. So you have S0 and a corresponding Y value. Okay, so here you know that your inputs are D0 and then D1. Okay, and then from here we are going to ask ourselves, what are our select lines right here? So our select lines, why I'm coming, let me finish doing it. And then our corresponding Y value. So our D1, we can have, let's say 0, 1, 0, 1. Here we have 0, 0, 1, 1, just like what we do for every truth table. So if our select line, okay, please, our select line determines which particular data line will be routed as our output, or will be forwarded as our output, or selected as output. So if S0, if S is 0, so assuming our S is 0, what do you think is going to happen? S0 will always correspond to our first data line, which is D0. Okay, so whenever S is equal to 0, our D0 is selected. And if S equals 1, then our D1 is selected. This is how maths always works when it comes to selection. So the input signal, okay, at your selector will always determine which particular inputs will be forwarded as your output, okay? So you ask yourself, what is the binary value of your select line? If it is 0, then it means D0 will be selected. So Y will be equal to D0. If S is 1, then D1 will be selected. So Y is equal to D1, just as simple as that, okay? So there is no need having to draw all possible combinations for D0, D1, etc., etc. We can just simplify our truth table as this, or as follows. So our S, and then which particular D value will be forwarded as an output. So we will name this S and D. So if our selector is 0, then we know D0 will be selected. And if our selector is 1, then we know D1 will be selected. So that's our simplified truth table for our 2-to-1 max. Okay. And you realize that that was quite direct and simple. So if we are dealing with our 4-to-1 max, let's illustrate this also quickly. So if we are dealing with our 4-to-1 max, we are going to have this here, 4 inputs in the form D0, D1, D2, D3. And then our selector, we have S0, S1. Okay. So if we are drawing our truth table, here our S is 2, we have S0, S1. And we have to determine which particular D value or which particular data line will be forwarded as our output, or will be selected and forwarded as our output. So we look at the corresponding D value, okay, or the corresponding data line. Let me just illustrate that as D. So for S1, we just have our 0, 1, 0, 1, and here we have our 0, 0, 1, 1. So if your S0 is 1, if your S0 is 0, okay, that's for the first combination. S0 is 0, S1 is also 0. Please, which data line do you think will be selected with this combination? Yes, can someone help us? Are we together? Um, hello. Hello.
Yes, hello.
All right. So, please, did you get a question, or I should take it again?
Yes, please.
All right. So, I was saying that for a 4:1 max, we have two selectors, which is S0 and S1. So we first illustrated with a 2:1 max that if S0 is 0, we know that the binary connotation of 0, or if we are to convert our binary number 0 to decimal, we know it's equal to 0. Okay. So that what 0 is trying to tell us is that we are going to select our data line 0. Okay. And then if S is equal to 1, we know we are going to select our data line 1. Okay. So for two select lines, we have our first combination to be 0 and 0. So if our first two combinations are 0 and 0, which particular data line are we going to select? If our two select lines are 0 and 0.
Is it data line 0?
Exactly, we are going to select our D0. Okay. Why? Because both S0 and S1 are both 0. So if they are 0, we know that the binary connotation of 0 and 0 is just 0. So that corresponds to data line 0. But if we have 0 and 1, which data line are we going to select?
I would say line 2. Line 1, line 1.
1. So we are going to select D1. Why? Because 0 and 1 is just 1. So we can match it up to D1. And then if we have 1 and 0, what are we going to select?
Then we select 2.
We select D2. Because we know that 1 and 0, if you convert this to decimal, that's just 2. So you select your corresponding data line. And then you have 1 and 1. So 1 and 1, what do you select?
3.
3. So you are going to select your D3. Okay. So this is the simplified truth table for a 4:1 max. And from the same logic, you can go to 8:1 max, or whichever max you want to work with. Okay. So let's take one last illustration, and then for, let's say, 8:1 max, and then we can close the class. So let's take 8:1 max. This is quite serious than the previous example, but let's try that and see. So we have an 8:1 max. And then after this, I'm going to ask 3 different questions on what you've done on max. And then you can, so we have 1, 2, 3, 4, 5, 6, 7, 8. So we have D0, D1, D2, D3, D4, D5, D6, and then D7. And we are going to have one output, which is our Y. So for an 8 to 1 max, how many select lines are you going to have?
3.
This select lines is correct. So we're going to have 3 because 2 raised to the power 3 gives us 8. So we have S0, S1, and then you have S2. So to draw our truth table, we know we are going to have our S0, S1, S2, right? And then we have to look at their corresponding D values or the data lines that will be selected. So here we have 0, 1, 0, 1, 0, 1, 0, 1. So here is 0, 0, 1, 1, 0, 0, 1, 1. And then we have 0, 0, 0, 0, 0, 0, 0, 0. Okay. So combination 1, if S is 0, S1 is 0, and S2 is 0.
Why are we having all zeros for the line 1, line 0?
Oh, okay, so oh no, please. That was an error. Sorry, I didn't look at that. There's supposed to be 1. Okay. So we are supposed to have 4 zeros and 4 ones. Thanks for drawing my notice to that. That was an oversight. All right, so we have 4 zeros and 4 ones. Sorry. So I'm going to have 0, 0, 0 as our first input combination. So if our first input combination is 0, 0, 0, which data line will be selected?
Line 0.
Please come again.
Data line 0.
Okay, so we have
D0.
D0, right? Then 0, 0, 1, which data line will you select?
D1.
D1. Then we just proceed in that manner, D2, D3, D4, D5, D6, and then D7. Okay. So depending on the input combination you are given, you select the corresponding data line. So this applies to all types of multiplexers. This is just how their simplified truth tables look like. Once you're able to represent the input combinations, just number the corresponding D values from 0 to the highest, and you're okay. So you can be given a question that, let's say, let's say a 16 to 1 multiplexer or a 16 to 1 max has let's say selector inputs S0. If no, let's say, let me give the ways straight away. So we have, let's say, 1, 1, 0, 1. Okay, so these are S values. Which data line will be selected? Okay, So you can be given that, assuming the data lines are numbered D0, D1, etc., which data line will be selected if these particular values are present for your select line. So what we are going to do is I just convert this binary number for the select line into the decimal equivalent, okay? So to convert this into your decimal equivalent, you know that here you have 1 is raised to the power 0. So you have 2 raised to the power 0. That gives you 1. Plus here is 1, here is 2. So you have 2 raised to the power 2. That gives you 4. Plus you have 2 raised to the power 3. That gives you 8. So 8 plus 4 plus 1, that gives you 13, right? So you know that for this particular one, D13 will be selected for output. So your Y here is going to be D13. Okay, so this is just how to solve problems under multiplexers. Mostly the questions might try to test your understanding of how the select lines are determined. Okay, so how the relationship between your select lines and then your inputs. All right, so the relation between select lines and then your inputs, and then the relationship between the signals for your select lines and then how the corresponding data is selected for outputs. These are two basic fields that the questions might be centered on. Okay. So the next time, I hope we can meet tomorrow. If we meet tomorrow, we are going to look at how to draw the logic diagrams for your selectors, okay? For your multiplexers, I mean. And after that, we are going to look at the multiplexers. And then we are going to look at encoders and decoders also. All right, and then we'll be bringing combinational circuits to a close. And then after that, we are going to answer some questions together, okay, some MCQs together. Let's say about 50 of them under combinational circuits. And once we are okay with them, we'll move to sequential circuits also. All right, so thank you very much for making it to the end. We'll meet for our next meeting, hopefully tomorrow.